Let's talk about the area under the curve. We'll pick a simple example. This is f of x equals x squared, and it's shown by the blue line right here. Now, we want to calculate the area under the curve. We can approximate it by breaking up the interval that we're interested in this case 0, 1, into subintervals. And so in general, we'll think of our one endpoint as being a, and that's 0. The other endpoint as being b, in our case that's 1. And we're going to have n subintervals. In our case, it'll be 4. And then the size of the subinterval will be delta x is equal to b minus a over n. And so in our case here, our subinterval is of size 1 minus 0 over 4, which is a quarter. And so if we're interested in the area, there's a couple of different ways we can do it. So the first way we can do it is using what's called the right point rule, and using this region right here that I'm outlining to approximate the area. And the other way we can do it is use the left point rule and use the region I'm showing right here with the yellow pen to approximate the area. And so the right point rule says that r is equal to f of x1 times delta x plus all the way up to f of xn times delta x. And in our case, it would be equal to f of x1 times a quarter plus f of x2 times a quarter plus f of x3 times a quarter plus f of x4 times a quarter. The left-hand rule says that the area is approximated by f of x0 times delta x all the way up to f of xn minus 1. So we stop one short of the last one times delta x. And in this case, it'll be f of x0 times a quarter plus f of x1 times a quarter plus f of x2 times a quarter plus f of x3 times a quarter. So we could use either method to try to calculate the area under the curve. And of course, either method will be an approximation. But we can wonder what happens now when we let the number of subintervals get large. Under that circumstance, the size of the subintervals will get smaller and smaller, and both of these approximations will get closer and closer to the true value for the area under the curve. This motivates us to define the area under the curve as a is equal to the limit as n goes to infinity, and now I've taken the right point rule here all the way from f of x1 times delta x up to f of xn times delta x. So let's consider this problem for the curve f of x equals x squared on the interval 0, 1. And so we're going to do a calculation of the kind that we're doing over here, but we're going to let the subintervals get smaller and smaller. Now to actually do this calculation, we need to know a fact about sums, and that is that the sum of 1 squared plus 2 squared all the way up to n squared can be calculated exactly as n times n plus 1 times 2n plus 1 over 6. So we're going to use that in our calculation. So let's get started. We want to plug in here, and so we're going to take the limit as n goes to infinity of f of, now we actually need to know what to put in here, so let's calculate what x1 through xn are. The values for x1 through xn are x1 is equal to a plus delta x, x2 is a plus 2 delta x, x3 is a plus 3 delta x, all the way down to our xn is a plus n delta x, and that turns out to be b. Okay. So in our case here, a is equal to 0, b is equal to 1, and as we're doing the calculation over here, we need to choose delta x to be equal to b minus a over n, which is 1 over n. And so x1 will be 0 plus 1 over n, so this is 1 over n. x2 will be 0 plus 2 times delta x, which is 2 over n, and so on. So we can plug these values in here now. So we're going to have f of 1 over n times delta x, which is 1 over n, plus f of 2 over n times delta x, which is 1 over n, plus all the way up to f of n over n times 1 over n. Okay, so what's our function f? In this case here, our function f is x squared. So this will be the limit as n goes to infinity, 1 over n squared times 1 over n plus 2 over n squared times 1 over n plus all the way down to n over n squared times 1 over n. Okay, so continuing with the calculation, we notice that there's a n cubed in the denominator of each of these terms. And so we can pull that out. So this is the limit as n goes to infinity, 1 over n cubed times 1 squared plus 2 squared plus all the way up to n squared. So using the formula that we have up here, we can write this as the limit as n goes to infinity, 1 over n cubed times n plus 1 times 2n plus 1, all divided by 6. And so we can pull out the 1/6 if we want to. And so this is 1/6, the limit as n goes to infinity. And we can write this as n over n plus times n plus 1 over n times 2n plus 1 over n. Okay, so this is 1/6 times the limit as n goes to infinity, and we'll see the n over n will go to 1. The n plus 1 over 1 n will go to 1, and the 2n plus 1 over n will go to 2. And so this is equal to 2/6, which is equal to 1/3. And so that's a way to calculate the area under the curve for f of x is equal to x squared.